Hello, my name is Brandon Lewis. We have Joshua Amaro and Daniel Maruzzi. This is Lab 5. All right, so with our design requirements, the customer stated that they want a steady state error equal to 0, overshoot and undershoot less than 2%, rise time larger than zero point 0.1 seconds, and initial slope should be minimized in order to reduce jerk, and 2% settling time less than 2 seconds, and a voltage request to be below 24 volts. So with that, we had 5 total labs that we did in order to design our final controller. Labs 0 through 2 involved measuring certain characteristics from the motor so that we could derive a proper controller for the motor. And then in labs 3 and 4 involved testing certain controllers to understand how the effects of changing different KP, KI, or utilizing different controllers would affect the transient response. And then in lab 5, we actually designed the PID controller. So with our initial guess, we used a CISO tool in order to meet all the basic requirements with rise time, settling time, initial slope, and then this is our initial guess here. Obviously, that's going to change in real life, so we'll move on to our real iterations. Here's our KP, KI, and KD values as well. So our first iteration, obviously we see that there is a lot of oscillations, a lot of error, and some large overshoot. So in our first attempt, we reduce KI, and this is what we saw. So that overshoot was reduced, but the rise time was significantly decreased. So what we did is we dropped KI from 24 to 2, since that large of a KI value caused a lot of oscillations. And then this is what we got for that. So obviously we see rise time as well as settling time is decreased, and oscillations were very large with these. So we decided to increase KP to 10. And then with that, we got an increased settling time, increased rise time, decreased overshoot. There was a reasonable amount of error in there. We saw that it was relatively good, but we wanted to change some of the values just to make it a little smoother. So KP was lowered from 10 to 2, and KI was increased from 2 to 4. And then on fifth iteration, rise times decreased, settling time decreased, but a bit more noisy with that changed. So we changed KP from 2 to 4. And then on this one, since we changed KP, we saw some massive oscillations. So we increased, or we lowered KD from 1 to 0.02, and we saw this much better graph here. So that resulted in the oscillations removed. We did see this small overshoot here, which we didn't really like. And so tau F was changed. Didn't see too much of a fix in that. And we saw more oscillations. So then tau was reduced and it fixed just about everything. And this was our final iteration. You can see here that the overshoot's gone. Most of the error in oscillations is removed. We got good rise time, good settling time, and all that. So the pros and cons of a PD controller. So pros, reduce response, output quickly. Gain can be increased to change steady state error if you want to change that, and then easy to stabilize with the pre-filter to reduce some of those errors. And then with the cons, it's really noisy due to truncation error, and steady state error will never reach the desired value due to the equation for steady state error and the fact that you don't have a pole at the origin. And so then with a PI controller, the pros, 0 error due to that integrator, that 1 over S value. And then it reduces settling time by increasing proportional constant. So obviously we can change that if we need to. But the cons is that there's natural oscillations due to it remembering the old system and the area of that. And then there's still obviously noise in the system with this. And so then why did we choose a PID? It's kind of the best of everything. We can change all the values for KP, KI, KD. And with that, the integrator leads to zero error. The derivative will help control overshoot. The proportional controller will allow increase in rise time, and we have more options to meet those design requirements.